Hello everyone, and welcome to the design presentation of Project March. Now I know in the excitement you might have some questions, but please leave them till the end where they will be answered in the foyer. Please keep your phones on silent, turn the flashes off, and sit back and relax and enjoy yourselves.
$9,601. That's my average step goal this week. These days, more and more people are wearing their smartwatches and are going for that extra walk to fulfill their daily step goal. Did you reach yours today? Our daily step goal have become more relevant these past few years because we were stuck in our homes, behind our laptops, day in, day out. Our physical activity was at a minimum. Multiple campaigns have been launched to make people move again during the lockdown. For example, you could download an app to earn rewards by walking 20 minutes or more. And even now, NS is advertising walking routes at every station to invite people to explore the city and its surroundings. It's all about getting on your feet again. But what if you're wheelchair bound? 13,000 people in the Netherlands have a spinal cord injury. Spinal cord injury entails that your nerves are damaged on a certain height of the spinal cord. Below this location, you'll have no sensation nor control over your muscles, and therefore these people are wheelchair bound and not able to get back on their feet. My name is Lieke, and I'm the team manager of Project March. Project March has one vision. We believe that we can use technology to improve the quality of life for people with a spinal cord injury. Every year, we design, develop, and build an exoskeleton. An exoskeleton is a powered robotic suit attached to the outside of the body. This enables someone with a spinal cord injury to stand up and walk again. We are giving them their mobility back. But it doesn't stop there. Walking in an exoskeleton also has an impact on our mental well-being, as it makes it possible to stand at eye level with our loved ones again. But it also has an effect on things that we don't see. It improves their blood flow and therefore their cardiovascular health. On top of that, it makes their muscles and bones stronger, and it even improves their bowel and bladder function. But how does an exoskeleton work, you may ask? Well, an exoskeleton is a technological representation of our legs. The frame acts as our bones and carries the weight of both the exoskeleton and the user. The human joints are mimicked by powered robotic joints, where the motors act as the muscles. To determine where these joints should move, we have special software that can determine when, how, and where the exoskeleton should move. The brains of the exoskeleton. And eventually, what connects them all, that is the electronics. And therefore, the electronics mimic the nerve system. Exoskeleton technology is still at its infancy, and therefore not ready yet for daily use. We believe that we can make an impact on society by creating more awareness around this subject. We aspire to show fellow companies what such a young student team can achieve. Every year, a new team comes in to take up this challenge. We are the 7th team of Project March, consisting of 26 students. We set our sights to study for a full year to completely focus on this project. We have a variety of backgrounds and studies, from mechanical engineering to medicine, and we come from a variety of places. Not only within the Netherlands, but also from Belgium, Greece, and Romania. And through these diversity of disciplines, interests, and backgrounds, we make sure every aspect is covered. Along with our inexhaustible motivation, and make an impact on the world. But we're doing this not alone. We get a little extra help. Because in our team, we have a 27 member. Our pilot, Koen van Zeeland. Koen just turned 35 and has a spinal cord injury due to an accident 9 years ago. He followed his rehabilitation process in the St. Maarten's Clinic, where he already set his first steps in an exoskeleton. Driven by his perseverance, he completed this process sooner than expected. Koen is not afraid of a challenge, and despite his spinal cord injury, nothing will stop him from following his dreams. And therefore, he can't sit still. When he's not working, he likes to improve his stamina in the gym or explore the city on his handbike. Koen also sees potential in the exoskeleton technology, and therefore he is as excited and motivated as we are to build the best exoskeleton possible, ready for daily use.
When we asked Koen what he would want to do with an exoskeleton, he told us that he would like to be able to walk to a coffee stand and simply get a cup of coffee. Now, for many people, this seems like such a simple thing, but it really is not so straightforward for everyone. It comes with a lot of challenges. My name is Janna, and I'm the project manager of this team. When setting our goal for this year, we thought about our ideal exoskeleton. What does our perfect exoskeleton look like? And how can we, as MARCH VII, contribute to that? In order to answer these questions, we need to take a step back and think again of why we're doing this. We want to improve the quality of life of people with a spinal cord injury by building an exoskeleton that can provide them with the best possible user experience. So who better to ask than the user himself? We work in close collaboration with Koen throughout the whole year, from the very first design choices to the final testing. And because of this, we can work towards a valuable goal, and we can design the exoskeleton for a good user experience. Walking somewhere and getting a drink can be more complicated than you'd originally think. First, you need to be able to walk in the real world, which is complex and consists of many different terrains and obstacles that might prove a challenge. On top of that, while having your drink, or when performing other tasks while standing, you would like to have free hands, rather than lean on the crutches. Further, we are striving for independence of the pilot, for example, when getting in and out of the exoskeleton. And, of course, you'd want to fit well in the exoskeleton and look sharp. Ultimately, our ideal exoskeleton would be ready for the real world. It would be adaptable to different environments, and it would be comfortable and user-friendly. Luckily, we are not starting from scratch. We have a substantial base to work on, as there have already been 6 previous March teams who built their own exoskeletons. Each year, they made new improvements to achieve their own ambitious goals. The first 5 teams worked towards the Cyberthon. This is a competition where human and machine come together. The Cyberthon is centered around assistive technologies that can help people with a disability to perform everyday tasks. So those first 5 teams designed their exoskeleton in such a way that their pilot could overcome different predetermined obstacles, such as walking stairs or going through a door. The 6th team shifted focus. They took a big step and decided to go outside for the first time. They implemented depth cameras for measuring obstacle dimensions, such as curb or stairs height. The pilot would then inform the exoskeleton on the type of obstacle in front of him, so that the right walking pattern could be configured for the estimated obstacle shape. We believe that we need even more flexibility. And in order to accomplish that, we need to make the exoskeleton smarter. The fact that exoskeletons require input from the pilot on the obstacle type is currently a limiting factor. Unknown and unpredictable terrains may require each step to be different, which should be possible without pilot input. And you simply cannot beforehand make the perfect walking pattern for each type of terrain that you could encounter in the real world. We want to remove these limitations. We want to be able to step anywhere and make the whole experience more seamless. We want to lose the need for prior knowledge of what's ahead of you by not using pre-programmed walking patterns, but by creating them on the spot. In other words, to walk dynamically. Our team goal this year is to build an exoskeleton that enables our pilot to walk a pedestrian route. And we want to do this by continuously generating those walking patterns, which will be based on the exoskeleton's perceived surroundings. This is the goal we set up for ourselves in August. Since then, we've all been dedicated to realizing this ambition. And I'm very proud to present how all our hard work has resulted in the design of the MARCH VII.
together so nice. We acting so impolite, like we gon' call it a night. I call the call it a night. But first, I wanna see you walk that walk. Yeah, baby, walk that walk like. Ooh, sucker, walk that walk like. Oh yeah, I wanna see you walk that walk.
So now you've all seen how it looks, but what about how it actually works? For the rest of this presentation, we will tell you all about those technical features, and we will explain how they combine to achieve our goal. How the software can continuously generate walking patterns based on its surroundings, how the mechanical elements enable our pilot to walk, and how our input methods and tailored hardware features improve user experience. We shall begin with the core logic of the exoskeleton. We aim to mimic the body's amazing ability to subconsciously analyze the environment and determine where best to step. And doing all of this within a fraction of a second.
If I would have asked you to walk into this hall with your eyes closed, you would have probably felt quite uncomfortable. This is because we rely a lot on our vision to determine how we can walk around new unknown spaces. To help an exoskeleton to walk as freely as we do, it is thus really important that you make use of as much visual information as possible. Last year, depth cameras were introduced to help Koen cross certain known obstacles. But this year, we're planning to use the same cameras to walk anywhere we want. My name is Tuin. I'm one of the software engineers this year. And our goal is to help the exoskeleton actually understand where it can walk. We created a computer vision algorithm with which it can determine exact positions in any environment where it can safely place its feet. The algorithm starts with depth cameras that are placed on the top of the upper legs. These are used to map the world around the exoskeleton to a point cloud, which is a collection of 3D points that represent something, like a staircase. The algorithm looks in such a point cloud and tries to find areas that are reasonably flat and large enough to place your entire foot. It looks for such regions around the point we would first consider to be the most natural to step towards. But it may not always be the case that you can step exactly on this point. And that's why the algorithm also looks around it to see if there are any alternatives. And once an alternative has been found, it is proposed as the next position to step on to the whole exoskeleton system. Note that we use this single algorithm for all kinds of terrains, from level ground to ramps, from irregular terrains to even staircases. So the exoskeleton uses cameras to find this point, but how does it exactly know how to move to that point? And for this, we're now working on another flexible algorithm that can compute the exact joint movements necessary to end up in this position. The walking patterns we generate with this process are what we call dynamic gaits. To exemplify, take this scenario where you make a step on top of an obstacle from flat ground. We know our starting position, and we also know where we want to end up, as we just determined with the cameras. First thing we do is add a middle position to enforce that the exoskeleton lifts its leg up in the air so it doesn't brush over any object. The dynamic gait algorithm now consists of 2 stages. In the first stage, we compute all the angles of the joints in each of these 3 positions. We do this using an inverse kinematic solver that we built from scratch for this particular frame. And in the second stage, we compute the actual joint movements necessary to satisfy these angles. Using interpolation, we create smooth joint trajectories that start and end at the angles we just found. And these joint trajectories are eventually transformed to the actual physical movements via the control system and eventually the joints. Next to visual information, we're also planning to use tactile information in the shape of pressure soles. These are sensors placed in the soles of the shoes that can detect when and how much pressure is placed on the feet by the pilot. We plan to use this information when scheduling the movements of the exoskeleton. So let's say you can only swing with your right leg if most of your weight is on your left leg. Using this knowledge would make the exoskeleton much more predictable and also safer for the pilot. Because as the pilot, you want to be in total control of the exoskeleton, especially when you initiate a movement. Imagine you're in a driverless car, but there's no steering wheel, no pedals, not even a speedometer. I would feel pretty uneasy driving in such a car, purely due to the lack of input and feedback from the entire system. And to avoid such an experience for the pilot, we provide him with an input device. This input device is mounted on the right crutch and is the main communication medium between the pilot and the exoskeleton to give commands and receive feedback. This year we completely redid this device. And it's the first time we used a smartphone as the core device for the input device. The benefits of a smartphone would be having a large screen, a long battery life, they're accessible to write software for, and I assume everyone has one in this room. Coincidentally, we also made the first wireless input device of Project March, thanks to the smartphone. Via an app, the exoskeleton can give feedback about its status to the pilot. It can tell you, for example, in what kind of mode it is currently, what the battery life is of the exoskeleton, of the smartphone, and maybe it will even give you a step count. The pilot can select what kind of mode he wants to use or what kind of movement using a scrolling wheel, similar to one you would find on a mouse. We have done all these things to try to make the human-machine interaction as seamless as possible. But there is another piece of technology that would making the control of an exoskeleton even more intuitive. And that is the use of electroencephalography, or EEG. EEG is a piece of technology with which you can measure the brainwaves of a pilot. And using classification algorithms, you could determine whether a pilot wants to start walking, stop walking, or maybe sit. And using this technology, we could open many doors to an eventual hands-free experience with our exoskeleton. So until now, I mainly discussed the software and the input that the exoskeleton receives from the pilot and from the environment. But what about the actual output, the movements? The components of the exoskeleton that make it move are the joints. Each leg has 4 directions of movement, which are supported by 2 different types of joints. The first type is the rotational joint, which can be found in the knees. And the second type make a translational type of movement, which is used for the ankles and for the hips. Of these 2 types, the translational joint has seen the largest improvement in our year. We made them much stronger by improving the core actuator with a custom motor design, which is powerful and yet still fits our strict size constraints. And we also replaced the lever arms and the spindles for a larger range of motion. All of this has resulted in joints that are more than 3 times stronger and have at least 15% larger ranges of motion. Despite all these improvements, we would have still had an issue with a motion called the push-off. When we walk, part of our step involves literally pushing off your body with your hind leg. This push-off creates extra momentum, which helps maintaining a natural walking pace. However, shifting the weight of man and machine requires a lot of force that the previous ankles could not handle. And we decided to solve this with a rather intuitive piece of technology, namely the use of springs. Springs have the huge benefit that they can store large amounts of energy that can be released when necessary to lift all that weight. But they also give the benefit that you can still move your joint freely around as you would have done before. The only thing is that they are much harder to control than just simple rotational joints. And that's why we make use of a more advanced control technique known as model predictive control. With this technique, you create a model of the joint, and you use this to simulate how much current you need to send to the joint to move it to a certain position. And using this technique, we can move even these kind of joints with as much precision or control as you require. All these things would, of course, not be possible if you didn't have the proper electronics to support them. And the focus for electronics this year was to mainly improve the reliability, the safety, and to reduce the size of the components. A lot of electronics have seen changes in the exoskeleton this year. For example, the power distribution board has been refined to deliver more stable power to the components that require it and to have a better temperature control. Additionally, the communication boards have been completely redesigned this year and allow for a much more reliable message passing system throughout the network of the exoskeleton. And finally, we also added temperature sensors, which are placed on the joints and on some other key locations. And these sensors are used to avoid any hazardous situations or maybe even irreparable damage. In my opinion, these sensors are a great addition because the last thing I'd want to see is smoke coming out of this exoskeleton. And with all these improvements in safety and reliability, we have made a large step towards an exoskeleton that is much more ready for daily use. But what other things do we need to reach this goal?
To make an exoskeleton part of the daily routine of a person with a spinal cord injury, it needs to be user-friendly. It not only needs to be comfortable and easy to use, but it must also be easy to work with as an engineering team. My name is Lauran, and I am one of the frame engineers of Project MARCH. When creating a prototype, you want to have quick access to all cables and electronics that are attached to the bones. For this, we developed a new concept for the electronic trays, where the cables are neatly stowed away behind a hinging door onto which the electronics are attached. This design decreases the risk of damage due to incorrect clamping of cables or touching of components. And it has the added benefit that electromagnetic interference is reduced. The next step is incorporating solutions such that the pilot can independently put on and take off the exoskeleton. Let's walk through the steps that a pilot must undertake to get ready for walking. First, the pilot must attach himself to the exoskeleton. We do this by means of fixtures. These go around the legs and the stomach of the pilot, and they carry his weight. They also help guide the limbs to follow the movements of the exoskeleton. This year, we want the pilot to be able to close all fixtures himself. He must do so while sitting, and thus needs the freedom to lean forward. By making the torso fixture both lower and go less in front of his stomach, the pilot has the freedom he needs to lean forward and adjust his leg fixtures. On top of that, we want the pilot to be able to wear his daily footwear in the exoskeleton. By customizing the shoe and incorporating a click-on system in the sole, the shoe can simply slide into place, after which the heel is locked onto the exoskeleton footplate. To release, you can simply use the release handle that fits onto a keychain and pull at the back of your shoes. This way, the pilot can put on a pair of shoes in the morning, and he does not have to take them off until he returns home. Now that we have looked at how to get into the exoskeleton, we can look at how our new design improves the actual walking experience. The new backpack design allows for more freedom of the arms, and through researching the optimal stance of the joints, the center of gravity of the exoskeleton is shifted closer to that of a human without one. The closer this center of gravity is to the natural center of gravity, the less effort the pilot will need to remain upright. We see a future for exoskeleton technology where doors are opened for people with a spinal cord injury. Perhaps one wants to go to a cafe to grab a coffee. During moments like these, you want to be able to stand without the need for crutches. However, balancing an exoskeleton with a person that's freely moving his upper body proves to be pretty challenging, as the external input of the upper body movement is hard to predict. We developed a mechanism that allows the crutches to be attached at the front of the exoskeleton to help create a stable base and allow the pilot to have his hands free. Lastly, we want to step outside at any moment. However, electronics are not pleased with any weather scenario. Our engineers have incorporated smart solutions to help create a splash-proof design by making the parting lines of the covers overlap, by including seals, and by limiting the open areas near the joints. Water cannot seep in. And if water does seep in, we included gutters in the covers to help guide the water back out. With all these additions, we make steps towards a future where daily use of an exoskeleton becomes second nature.
There are many more advancements, additions, and alterations that we could not include here today. But what it ultimately comes down to is that Project March exoskeleton has evolved to be more easier to use, walk more naturally, and be able to tackle the real world seamlessly. I want to thank you all for being here today, and I want to extend that thank you to those who watched online. I want to thank our partners, without whose generous contributions and invaluable insights our project would have not been possible. And last, but certainly not least, I want to thank the team for their devotion to Project March. With our final design, we will now start building and testing this incredible piece of technology. We want to invite you to join us on the final event on the 19th of August. By that time, Koen is able to walk anywhere he wants and get that cup of coffee.
Trust, yeah. No, I don't wanna waste what's left. And on we'll go through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go through the wastelands, through the highways, and on.
Hello? Hey. Hey, good afternoon, evening, everyone. Thank you for coming. I think we're really happy to be here and to have been able to present this to you. We're now going to move to the foyer for the balls, and we would love to have a talk with you and discuss everything we've done till now. So see you in the foyer.